Alright, so this projectile motion problem is different from the first one in that now the initial velocity is actually at an angle to the horizontal. That angle is given to us at 40 degrees, and now the initial velocity is 11 meters per second. So let's say we have a cannon that's firing a cannonball, and we want to know three things. How much time is it in the air before it strikes the ground? We want to know what is the maximum height that the cannonball reaches, and we want to know what is the range of the cannonball. Okay, so let's put these different questions into terms that we understand. Maximum height as well as time are both dealing with the y-axis. Okay, when we're looking at the range, now we're concerned with the x-axis. So let's go ahead and break up what we are given into our components. For the x-axis, we know that we have an initial velocity that actually has both components, x and y. So we need to come to a conclusion about what is the x component and then what is the y component. So looking at this, I can see that the x side is my adjacent side. So that means I'm looking at cosine, right? Because cosine of an angle is equal to the adjacent side over the hypotenuse. And here my hypotenuse is simply that total initial velocity, which includes both components. If I were to look at the y component now, that is the opposite side. And so I know also that sine of any angle is equal to the opposite side over the hypotenuse. So I can use both of these to break this up into components. So in order to solve for the adjacent side, it's going to be the hypotenuse, or the entire magnitude of velocity, which is 11 meters per second, times the cosine of the angle, which in this case is 40 degrees. If we look at the y components, and this is the initial velocity for the x direction. If we look at the y, and we want to get the initial velocity for the y direction, it's going to be then 11 meters per second times sine of 40 degrees. Okay, so now I have expressions for both initial velocities. If we want displacement, right, that would be delta x, and we don't know what that is yet. In fact, that's what we're asked to solve for last. And delta y, our total delta y, is 0 because it's going to land on the ground, and we're going to assume it's being shot from a height of 0. Okay, so here our delta y total is 0. We can also solve for y max, and that's something that, again, we're being asked to solve for. So we're not sure what that actually is as of yet. Okay, some other kinematics things we might want to know is the acceleration. And since we're neglecting air resistance, we know that the acceleration in the x direction is 0. The acceleration in the y direction is due to gravity. Okay, and so let's go ahead and define the down direction as negative. So my acceleration is negative 9.8 meters per second squared. You could also substitute 10 for the 9.8 since that's allowed on the AP exam. So let's solve the first question. Okay, I'm going to switch to black. We want to know how much time is this cannonball in the air. Okay, so if we look at the delta y equation, which a lot of you like to use, I like to use it as well. If we look at this equation, having a delta y equal to 0, we can plug that in. We do have an initial velocity for the y direction, and we do have an acceleration. But that leaves us with a quadratic equation to solve, which unless you have an n-solve function on your calculator, you wouldn't be able to do without breaking into the quadratic formula, and that seems like a waste of time. When we can break this up and specifically focus on the time it takes for the cannonball to go from the initial position up to the maximum height. Okay, and so if we just look at that first half of the motion, then we can take that time and multiply it by 2 to get the total time that it's in the air. So let's try that. We're going to use v final equals v initial plus acceleration times time. We can get rid of v final because we know at this top point in the projection, the velocity is going to be 0. So now it's a matter of just rearranging and solving for time. T equals a negative initial velocity over the acceleration. And so we're going to plug in our value for the initial velocity. So let me go ahead and multiply that out. Sine of 40 degrees times 11 gives me 0.95. Oh, that can't be right. I did something wrong. Okay, sine of 40 times 11. Oh, that's much better. 7.1. Okay, 7.1 meters per second. Let's plug that in. So we have negative initial velocity, 7.1 meters per second, over the acceleration, negative 9.8 meters per second squared. Okay, see how those negative signs cancel each other? We're going to plug that in to our calculator, and we get a time of 0.72 seconds. Okay, remember to keep those units in there. So now we've answered this question. T equals 0.72 seconds. Are we done? Oh, wait a minute. Remember, this was just solving for the first half. So we actually have to multiply this by 2. And we get 1.44 seconds. Okay, so we do have our total time that it's in the air. I'm going to erase these calculations so that we have room for the next ones. Okay. Next we want to solve for the maximum height. Okay. How would we do that? Well, now that I know the time, now I can use my delta y equals initial velocity times time plus 1/2 at squared. But I'm not going to apply it to the entire motion. I'm just going to apply it to that first half again, okay? So, because I want to know what is the delta y during that first half of the motion. That would give me my maximum height. So instead of using my total time, I'm just going to use the time it takes to reach that maximum height, which is what we had solved for initially and then multiplied by 2. So it's 0.72 seconds here. So it's really important that you don't just start plugging and chugging different numbers in different places. You really have to understand what's going on with the motion and break it up into its different parts. So now I'm going to plug in for, actually we're solving for delta y. Our initial velocity is still 7.1 meters per second. We're going to multiply by 0.72 seconds plus 1/2 times the acceleration, negative 9.8 meters per second squared, times time squared, 0.72 seconds squared. All right, let's go ahead and plug that into our calculator. We get 7.1 times 0.72, about 5.1. 9.8 times 0.5 times a 0.72 squared gives us 2.5 about. And so it's 5.1 minus 2.5, right? Because that will be a negative number. 5.1 minus 2.5. I should have been able to do that in my head. And we get 2.6 meters. So that's our maximum height. 2.6 meters. Okay, almost there. Let's get rid of this now. Okay, finally we're looking at our range, and now again we're concerned with our x components. See, now we get to use all that work. Okay, so delta x equals the initial velocity times time plus 1/2 acceleration times time squared. Okay, good news, the acceleration is 0. So this whole term right here goes away. Now, the time that we're looking at is the total time that it's in the air. We don't need to break it down into halves at this point, right? Because we want the full delta x, the full range. So we need the entire total time. So we're going to use 1.44 seconds as our time. So delta x, or the range, is equal to the initial velocity in the x direction. So now let's go ahead and plug that in. Cosine of 40 degrees times 11. Let's let's try that again. Cosine of 40 degrees times 11 gives us 8.4 meters per second. Okay, so it's 8.4 meters per second times our total time, 1.44 seconds. Plug that in, and we get a total range of 12.1 meters. Okay? So it's pretty simple, it's not too complicated, as long as you're breaking things up and keeping the two axes separated and straight in your calculations. I'm trying to stop the recording, I really am.